Okay, ladies and gentlemen, today is the first strength of material, first week of the strength of material course. We will start with general information of the strength of materials, and we will talk about the subjects of the strength of material, why we use this strength of material. We will talk about that. After that, we are going to talk about the fundamental concepts that we will use in the next stage in our calculations. Let's get started. I'm gonna share my screen, whiteboard. Okay, here we go. Yes, change this part now. Here. Okay, firstly, I would like to start with the subjects of the strength of material. Let's write, oh, sorry. Subjects of materials course. Okay. We will learn how to design the structural members. Design mean, let's say we have a beam. By the way, let me explain that here. Let's say we have a beam here. This is a simple beam. Yes, on top of this beam, we have a uniform distributed building. Uniform distributed load, sorry. As you can see here. Okay, the question is, what size and timber beam can we use for this beam? Okay, we will determine the size of the structural members. Design means to determine the size of the structural members. Okay, what we are gonna do, we are gonna design structural members. Or that means determine the size of structural members. Okay, let's say we have a beam like this. For this is my section. Let's say this is 20 centimeter. Here is 10 centimeter. I'd like to use this section for this beam. Okay, so if I know the section, I can calculate the capacity, load carrying capacity. Then check with the internal force that comes from this simple beam. So if my capacity is greater than from the internal forces, okay, I can use my section. So that means if I know the section, in strength of material, we can calculate its capacity, its load bearing capacity, load carrying capacity. Okay. If we know the size of structural member, we calculate the load bearing capacity of the member. In the first one, we don't have any size. We determine the size. In the second one, what we do, if we know a size, we can calculate its capacity and then check it with the internal forces and select if it's appropriate for that situation. Okay, here what we do under this loading condition, again, let's talk about the simple beam. We have under this loading, our structural member beam will get some deformation and it will have this shape. Okay. In this course, we can calculate this deformations. So deformations and strains, or we can say deformations, are calculated or could be calculated in this course of structural members under different loading condition. Okay, we can change this uniform distributed load. We can put here a triangular distributed load instead this one. So again, we can calculate the deformation. And the last one is you know, all our structures should be in balanced position, but sometimes we have some stability problems. Stability problems means if we use thin members for loads, our members make some deformations under loads, and suddenly the system fail and can't carry any more load. To avoid this type of problems in our structures, we make some stability checks. In this course, we are gonna see that end of, I guess we are gonna do this at the end of the course, yes, but we will do it. We will do stability checks. When we do that calculations, you're going to understand the stability checks, what it means actually. Okay. Okay, these are the 4 subjects that we talk about in strength of materials. Let's go ahead. Let's talk about the fundamental concepts of the strength of materials. Just a second. This is page 2. Okay. Oop. Fundamental concepts. Okay, now we're gonna talk about the uh, behavior of a member under a force. Okay, for example, I'm gonna draw you four different graphs. The first one is this. This is second one will be here. 4, 3, and 4. Okay. The vertical axis is force F. Okay, this is force for each one. And the horizontal one is epsilon, strain. Strain in Turkish şekil değiştirme. It's a kind of deformation. Okay. Now, let's think about a structural member here. We applied a tension to this member. Under this tension loading, it's gonna get elongation. That means its length will increase a little bit. Okay. We slowly, by the way, okay, we are applying this F to this member, but slowly we are increasing the force. Okay, for force increase, deformation increase, force increase, deformation increase. Okay, so that if we draw this on the curve, okay, like this, until this point, as you can see, force increase, deformation increase at the same time. Okay, until this point. After this point, we start to reduce the force. Okay, we are at this level. We slowly reduce the force. This, not suddenly take that force out. Slowly, we are reducing the force. And this deformation goes back to its initial position. Okay, so at the beginning, what was our deformation? It was 0. We started our curve from this origin point. Force increased, deformation increased. At this point, yes, I have this deformation. That's okay. But when I reduced slowly the force, this deformation goes back to initial position and it gets 0. So like this, it goes back. Here, first was like this. We went in this arrow direction, and in the second application, we returned back in this arrow direction. But at the end of the day, when we remove all load, we are at the same point where we started. There is no deformation. Deformation is 0 when we take out all the loads. So we call these type of members elastic. This is elastic. If there is a return back, this is elastic. By the way, if that goes back to the initial position, it's elastic. This definition is better. And now we have one more loading, one more member. Here we have a member. We applied tension force. We start to apply this tension force from 0 to the maximum level. But at the same time, while we are increasing the load, our deformation increase. Okay. My new member length is like this. That means same like that here. Okay, until this point again, I followed this red line. My force and deformation increased. That's okay. Now I slowly released the force and started to reduce the force slowly, step by step. So what I see here in this member, okay, when I reduce the force, this increased length reduced to this level. But at the end, when I make my force 0, I have this deformation. At the beginning, I have this level, but after this loading, okay, I get 0 back, 0 force, but at the end, what I get? This length. The maximum length a little bit reduced, okay, that's okay, but it didn't get completely 0 here. So this curve is like this. Okay, I'm here. The formation will a little bit reduce. But at the end of the day, this is the maximum deformation. I'm not at the maximum deformation, yes. But when at this point, my force is 0. There is no force here. But that means there is a permanent deformation on the member. This part shows us the permanent deformation. Remember, this is F, this is epsilon strain. That means deformation. So how do we call this type of members? We call these type of members elastoplastic members. Elastoplastic members. This was elastic. Permanent deformation means, by the way, plastic deformation. Okay. Plastic deformation is a kind of permanent deformation that occurs on our structural members. We call this elasto because we were at this point and at this deformation level. When we remove all the loading, our deformation reduced. This means elasto means, okay, we went back a little bit, not to the 0 initial position, Okay, we went back, but still there is a permanent deformation on my structural member. Elasto says, okay, I went back a little bit. Plastic, okay, I went back a little bit, but there's a permanent deformation on the structural member. This is the elastoplastic member behavior. Okay, let's talk about a new member. Okay, I have this material again. I applied this tension load. Again, from zero condition, I slowly increased the load step by step. So at the maximum point, let's say I get this length. I have this member. This is L last. Here, L first, let's say. Okay, let's draw the curve from this origin point. We increased load. Okay, we are now here. By the way, let me add the arrow here. Okay, we are at this point. Okay, we slowly remove the load on our member. But what we see in this member, there is no deformation change. Okay, we applied the load. Okay, we get a longer member. But when we remove the load, we have still longer member. This length doesn't go back to zero initial position or a little bit back. It doesn't go back. So we have a deformation at this maximum load point. So when we remove all the load, we have same amount of deformation on our structural member. So we call this type of material, this deformation is, permanent deformation. How do we call that? Plastic deformation. The name of this behavior comes from this plastic. So it's a plastic behavior. It's plastic behavior. We apply load, member length changes, it increase. When we take out the load, the last length doesn't change. There's a permanent deformation. It doesn't go back a little bit or completely. It stays like under loading. Okay. So this is a plastic behavior. And the last behavior is, it's almost similar to the first one. This is F, this is epsilon. In this member, we increase the load. By the way, let's draw the sketch again here. We increase the loading. Okay, the length increase. But at the end, when I remove loading again, it goes back to initial position. There is no permanent deformation on this member. But if this change is on a line, By the way, it's gonna be red. Okay. Okay. I go up there here. My force increase, deformation increase. After this point, I reduce the force, and in this path, linear path, the deformation goes back to initial position. So when I get zero force, I have zero deformation. There is no permanent, there is no plastic deformation on this member. But this behavior is almost similar to the first one, elastic behavior, but it works on a line. On a line, we call this type of behavior linear elastic. Or in the next step, we are going to see that this is a hook member. This comes from the inventor's surname of this behavior, Hooke's member. In the next stage, when we talk about the material steels stress strain diagram, we are going to see this hook behavior again. What we learned here, we learned we have 4 different behaviors in strength of material. Elastic material, we start from a point, we apply load, we increase deformation. When we remove the loading, we get the zero condition, initial condition. This is elastic. Okay, this is elastic. If this behavior occurs on a line, it's completely the same. Only the behavior is on a line. That's why we call this linear elastic or Hooke's behavior. Elastoplastic, what is the elastoplastic? Okay, when we apply loading, yes, deformation increase. When we remove the loading, deformation a little bit reduced, but there is still a small amount of permanent deformation, which is plastic deformation. That's why we call this behavior elastoplastic. In the plastic behavior, we apply loading, we go to the maximum deformation. That's okay under this loading. But when I remove this loading from here, deformation is still there. It doesn't change completely or a little bit. We have the maximum deformation. It's a permanent deformation. It's a kind of plastic deformation. That's why we call this behavior plastic deformation, plastic material, or plastic behavior. Okay. Okay, we learned these 4 fundamental concepts. In strength of materials, now we know all these 4 behaviors, but what we do in strength of materials? Let me write it next page. Okay, that's better. Okay, we are here. Okay, here we deal with homogeneous materials. homogeneous materials, we deal with isotropic materials, and we deal with elastic materials, linear elastic, by the way, in strength of material. As you can see here, we emphasize the linear elastic. You know what the linear elastic behavior. Now, in strength of materials, we deal with these type of members, materials, or structural systems. Okay, we're gonna talk about let me see. We have some theories for the strength of materials. We have some theories. I'm not gonna talk about the all of them. I will talk about only two of them. Principles, the major principles of strength of materials. The first one is principles of rigidity. Rigidity. To make our calculations, we make this assumption in this, which is given in this principle. Okay, let's say we have a structural system. We have a load on this member. Okay, so we will get a deformation like this. At this point. So what we do here in this principle of rigidity, under this loading, okay, this member gets a new shape like this. Okay, while I'm drawing these sketches, you know, I'm a little bit exaggerating. Okay, you don't see any structural member like this, by the way. But to show what we are doing, I'm a little bit exaggerating in my sketches. Under this loading, we get this new shape. So after we get this new geometry, new shape, what we assume that this deformed shape is a rigid member. Remember, what was the rigid member? Deformable member, when we apply a load to that member, it gets a deformation. But for the rigid members, there is no deformation. We apply load, we don't see any deformation on structural members. Okay, this is the main differences the between rigid and deformable member. Let me draw a sketch here. Here we have a box, one more box here. If we have a deformable member, our member will get squeezed here and its size will change. Okay, but for the rigid members, we apply this loading, no deformation. Okay, this is the main differences between the deformable and the rigid members. So in this principle, after deformation, system is assumed like a rigid system. And all um, all principles used in rigid systems could be applied to this system. We use some calculation methods for the rigid systems. Okay, after deformation, we assume this structural system is a rigid system. This deformed shape is a rigid system. So that means we can apply the solution methods to this new rigid system. Okay, that's why I'm writing this principle here. Other one is first order theory or principle, whatever. Birincisinin Türkçesi rigidleştirme ilkesiydi. First order theory is birinci mertebe teorisi. Okay. This means this. Let's say I have a beam again. I have a load on this member under this loading. I get a deformed shape, and this deformation is delta 1. And similarly, I have same beam here again. Here I have a different loading. Under this loading, I have again a deformation. This deformation is delta 2. Delta 2. Here we are dealing with the first order theory, and we know that this system or these members are linear elastic members. Okay, linear elastic. When we remove the loading, it gets back to 0 position. this path is a line. That's why we call this linear elastic. If we have totally F1 plus F2, if we are looking for the deformation under this total loading, we can directly sum delta 1 plus delta 2. This is the first order theory. Okay, this is the fourth order theory. Any questions so far? No. Okay. Okay. Here we are gonna deal with the frame members. Frame members, çubuk sistemler. Frame members, çubuk elemanlar. What is a frame member? Okay. Let's do the definition of the frame member first. You know, all our structural members are three-dimensional members, basically. But we know that one length, one size of this member is greater than other sizes. For example, I have a rectangular beam. Okay, this is this is a kind of three-dimensional member. That's okay. But as you can see, one dimension, which is the length of the member, this size, is larger than the section size. Larger than this depth or width. This is a kind of frame member. Okay, how we idealize these frame members in our structural system? For example, if I have a member let's say we have this is the circular section. This is a kind of circular section. Also, there is a circular section here at the end. This is our arbitrary structural member. It doesn't have a perfect shape like this beam, but we have here an arbitrary shape. What we do here, okay, we find the center point of this one and the other one. So at each section of this arbitrary member, we connect the center point of these sections to each other. For example, if I have a section at this point, this line goes from the center point of this circle. It's same for this point. It's same for this point. So we connect to each other all these section centers to each other. But at the end, what I get, at the end, I get a frame member. This is my idealized calculation member. Okay. This is my idealized calculation member. Frame members, we have frame members. Two types of frame members, depending on sections and depending on the axis. According to the axis, linear members. If this axis line, this line is linear, we call these type of members linear. It's if it's not a linear member, it's curved. So we have curved member. In this course, we are not gonna talk about the curved members. We will deal with always linear members. According to sections, we have two branches of frame members. The tapered sections. Tapered sections mean, for example, if I have a beam, I have, this is my beam, by the way, no. I have a beam like this. You can see my structural member change its size. It gets greater at the midpoint, as you can see here. We call this type of sections tapered sections. Okay, the section size changes. Or we have constant sized sections. So it's like this. There's no change on the section size. As an example, you know, the frame members, we talked about most of them in the statics course. For example, we have a simple beam. We have simple beam. We have simple beam with cantilever. These are only examples. Okay, you can see many different types of frame members. You can see continuous beams like this. Continuous beams. You can see frame systems. Or cantilever members, or truss systems, you know. These are some examples for the frame systems. By the way, there are a few examples here. Gerber beam, which is a beam like this. Maybe you can hear this one in your professional life. That's why I'd like to show you what it is. It's a kind of continuous beam. This beam has pins, zero moment points inside of the beam. For example, we have a hinge. This is a kind of hinge. This is a Gerber beam. What is the rule? Let me write here. Gerber beam. This beam has there is same number. By the way, just a second before write it, let me explain with one more drawing and then I'm gonna write it. Let's say, let's change the system. Okay, we have one hinge here, one hinge here. This is a kind of structural system. We use these hinges. Hinge means there is no moment at these points. But please give your attention to number of the hinges. The hinge number equals the number of the internal supports. We have two internal supports we can apply. We should apply at least two hinges to the structural system. Number of hinges equals number of internal supports. Okay, this is a special type of beam. Why we use this type of beam? If let's say we are doing a building on a site, if the ground conditions are not good, and if we are expecting in the future different settlements, settlement means oturma, binadaki oturma. If we are expecting different settlements, we use this type of beams on the structural system. At that time, when that settlement occurs on the structure, our beams rotates on these hinges. So it doesn't make extra internal force on my structural system. This is a kind of fuse for my structural system, actually. Okay, we talk about the frame systems and Gerber beam. You can hear about that. We're gonna talk about the stress. I'm gonna start it and then I will give you material skills stress strain diagram. Any questions so far, by the way? Okay. Okay. Stress. Okay, we will talk about stress. Let's say we have a member. Just a second. Okay, this is my member. Under different loading condition, my member is in balanced position. Okay. If we divide the section, the member from this line, what I'm gonna see, okay, I'm drawing the left part and I will see the section here. Okay. At each point of my section, I'm gonna see a force. Okay, a force. System is again in balanced position here. We call these forces on the section stress, or the better definition is stress, a kind of stress is force acts on per unit area. Okay, so here to calculate the force here, for example, these are the forces. We write limit. This is the area A goes 0. Area goes 0. The total P force over area. So at the end of the day, stress is force over area. Okay, I think you know this stress from the high school physics lessons. It's same, there is no differences. Force over area. Okay, force over area. This is stress, but we have two different stresses depending on the direction. Let me draw here. If this is my surface, I apply force this area. This is the area, this is the P. Okay, I can calculate these small forces which are for per unit area, you know, which is stress under this loading. What is the important thing here? If my force is perpendicular to area I'm dealing with, okay, stress is stress. what I'm gonna do the P over A here. This is axial stress. Or the better definition, we will, okay, let's talk about the axial in the next stage. Firstly, let's write normal stress. Normal means here the axis which is perpendicular to the area. Normal, the normal of the section, which is in this direction. Up. Okay, normal of the section is this. So that means sigma, we use Greek alphabet for to show this. Sigma is like G, like this. In different books you can see, sometimes you see like this in different books, but sigma is sigma, which is normal stress. When you see the sigma, what you're gonna understand, okay, at the end of the day, we are doing P over A, force over area. That's okay. But this force is perpendicular to area we deal with. Okay. So let's do the shear stress. Again, I have an area here, as you can see, nice and cool. Here I apply to this surface like this, P. I'm not perpendicular to this area. My force is parallel to this area. So at the end of the day, we are gonna see this type of small forces, which are the stresses per unit area. So we call this stress like shear stress. Okay, shear stress. We show shear stress with tau. It's like T. It comes from, again, Greek alphabet, as I said previously. Here, P over A. Here is the area. Why? Okay, at the end of the day, stress is stress. Force over area. Why we are making these differences? Why we are dealing with normal stress or shear stress? Okay, structural members have different shear and normal stress capacities. That's why we do this branch. Okay, stress is stress, but depending our forces direction, our load bearing capacity changes. If we have shear stress, we check it with shear stress capacity. If we have a normal stress or axial stress, axial, that means better axial, which is perpendicular to the system. We check it with the axial stress capacity. That's why we make this division. Okay. So at the end of the day, the calculation of the stress is the same, force over area. This is really, really basic. You can do it. Okay. It's 10:12. Let's have a break, guys. We're gonna be here at 10:45. Okay. See you guys.
Hocam sesiniz kapalı.
Oh, I'm sorry. Thank you so much. Uh, okay, we learned stress concept, what it is. It's basically force over area. This equation is really basic, but here you should remember that we have two different types of stress here. One is normal stress, axial stress, which is perpendicular to the area. The other one is shear stress. Let me write here, by the way. This is shear stress. Yes, which is parallel to the area we deal with. Okay, now we know the stress definition and stress types at the moment. Okay, to get the capacities of the structural members, we test it. Okay, for example, if we have a steel member, we apply tension test. What is the tension test? We have a specimen, small steel specimen like this. We apply tension, so till it breaks down from here. Okay. Here there is a trick. It's good to learn, I think. We have two different material type. One is a ductile material. The other one is brittle material. Ductile material is what? By the way, in Turkish, sünek malzeme, ductile material. Okay, ductile material, sünek malzeme. That ductile materials makes deformations under tension loads. For example, let me draw a big specimen here. Okay, let's say this is a ductile material. Okay, we apply tension. You know, it gets a longer position here. So while it's getting longer, there will be a necking at the mid part. You're gonna see like this. Just a second. I'm gonna draw it. I'm just exaggerating while I'm drawing, but in YouTube, if you write material tension steel tension test, you're gonna see this. Okay. Your steel material under tension load will get this shape. So some part of the section will get reduced. We call this part necking. It's like from our body, the head, body, and neck. Neck part is a narrower part of this connection. That's why we call this behavior necking. After if we increase tension load, what we are gonna see? We are gonna see a breakdown like this. Oop. Okay. We will see two pieces. What is this? If we see this necking and then breaking on a member, we call this type of material ductile material. Example, for example, the most common one is steel. Okay. Let's say we have a cube like this, and we apply again a tension load. This is a different material. Under tension loading, we don't see on this cube, we don't see any necking, any deformation. This deformation shows that, okay, I'm getting deformed, but at the same time, I'm gonna break down soon. Be careful. It gives an alert to us with this necking behavior. It says us, oh, be careful. We are gonna get a breakdown in near future. And then it breaks from here. But in this example, we have cube, we are applying tension. There is no deformation. There is nothing. We increase load, increase. And then suddenly, it breaks down. It doesn't give us any alert before the breakdown. We don't know when it breaks. So this type of materials are brittle materials. In Turkish, this is sünek. This is gevrek. So an example for this, the most common one again, concrete. Okay, this is the concrete. So if we have a brittle material, we don't use brittle material for tension loads because we know that they are gonna break down suddenly without any alert, without any information. They will do it. Instead, we use this type of brittle material for compression. If you apply compression tests to this material, you're gonna see a good compression capacity. So how we understand a material is ductile or brittle, we apply tension tests. If it gives a necking like this, like the steel, yes, it's ductile. We prefer ductile because ductile material gives us an idea before complete fracture. It gets deformation, and we understand that, yes, it's gonna fail soon. Be careful. But brittle materials fracture suddenly. It doesn't give an alert. We don't know when it breaks. So that's why we don't use this material for tension. We apply compression for these materials. For example, reinforced concrete. Reinforced concrete structures have two components. The first one is concrete, which takes the compression loads, and the second part, rebars or steel cage inside, it takes the tension. So reinforced concrete is a kind of composite material, because there are two types of material which works all together to carry all these loads. So concrete itself is really brittle material, but at the same time, steel cage, steel rebars, completely ductile material. We combine them, and with these two material, we try to make ductile structures. We always want to make ductile structures, okay, in our professional designs. Okay, now you know what is ductile, what is brittle. Now I'm gonna draw you the stress strain diagram of material steel after a tension test. In the screen, you can see at the left hand side, we see a tension test behavior. We are just showing the behavior, not giving a detail here. But in the stress strain diagram, I'm gonna give you some details. Let me draw the curve for you. Here, where is, no, not this one. Here we go. I have my notes here. Okay. Okay. Here, this is the stress. This is the strain. Stress. You know what stress is? Force over area. Stress. Here is a strain. It's unit deformation. This is a kind of deformation, you know. Okay. Now, when we apply load, we get a linear part like this. After that, here, this is another point, and here we go. Almost linear part. After this linear part, here is the fracture. Okay. Now, what we have, let's show the important points here. Okay. Okay. Okay, here when we apply the force, stress occurs, stress linearly. This part is a linear part. Okay, instead this, maybe this, instead I'd like to use this line. That's better. Okay, this is perfectly linear part. Okay, until this point, we call this point proportional limit. Proportional limit. Okay. In Turkish, orantılılık sınırı. This point is end of the linear behavior. Until this point, our stress and strain behaves like a linear. There is a linear relationship between stress and strain here. Okay. The regions, let me write here. This portion is linear region. After this point, the behavior stop, the linear behavior stops, but there is a curved behavior here. This point is yield stress. When we reach up to the yield stress, we increase load at this level. Although we increase the load, stress doesn't change, but at the same time, the formation change in this region. This is the yielding plateau. Okay, the stress doesn't increase, but the formation increase from this point to this point. We call this area yielding plateau. By the way, let me write this part, perfect plasticity. Or yielding. Yielding in Turkish, akma. Akma. Akma gerilmesi. Yield stress, akma gerilmesi. Okay. Okay, what we are doing here, till this point, the system yields. But after this point, suddenly my material carry on to move more load. You can see stress increase to a maximum level. This is the ultimate stress. We call this stress increase after yielding strain hardening. This part is strain hardening. In Turkish, this is pekleşme. If you take a look at the Turkish books, you are gonna see this part. This is linear region. This is akma bölgesi. Okay, this part is strain hardening after the yielding. Okay, after we pass from an ultimate stress, what we see, our curve heads down. Okay, stress reduced here until the fracture point, until fracture. Okay, this area, this portion is where the necking occurs. Remember necking. What was the necking? Necking was the area reduction of the test specimen under tension. This was the necking, remember. Necking occurs after this ultimate stress in steel. And after a while, after this necking started to occur, after a short while, it gets fracture. And this test stops. So we have 1, 2, 3, 4 portion on the curve. The first portion is linear portion, linear region. The second part, no increase on stress, but deformation or strain increase, significant amount increase can be seen at this region. After this point, steel again starts to carry some more stress. You can see stress increase up to ultimate stress. This increased region, this behavior is strain hardening. Here, this behavior is strain hardening. After the ultimate stress, necking occurs on the section, and this area at the necking region gets smaller and smaller and smaller, and then suddenly it fractures at this point. Okay. Here in the linear region, we have a angle here. The slope of this linear part, we have a linear relationship. Remember, stress and strain has a linear relationship. How we can write this equation? Stress equals E times epsilon. This is the Hooke's law. Remember the linear elastic material. In the first lesson today, we talked about the elastic, linear elastic, elastoplastic, and plastic behaviors. Remember the linear elastic behavior. What we said there, this is the Hooke's material. Hooke's law comes from here. It works only in this linear region. It works only in this linear region. Okay. Because here there is a stress and strain. Here there is something different. This is stress. This is strain. This is a different thing. E, capital E. What is it? Modulus of elasticity. Or in different books, you can see this like Young's module. What is this E? What is this E? This E is slope of this linear line. Okay, E is slope of the linear portion. Okay. over epsilon. So it's a material constant. It defines the material actually. Steel has a modulus of elasticity number. It is a constant value for all type of steel. Okay, so it's a typical material property. Okay, so this part, this linear region in this area, Hooke's law works in this area, in linear part. There is a linear relationship. This equation shows us linear relationship. Sigma equals E times epsilon. Epsilon. E is the modulus of elasticity. It is a constant value for steel. You don't have to memorize it. If we need, yes, in our subjects, we need that number. At that time, we are going to give you that number. But what it is, keep this in your mind. It's the slope of the first linear portion. Okay. Okay. What we have more? I'd like to give you a few examples regarding this E values, modulus of elasticity for different materials. Steel, E steel is GPa, gigapascal. E for aluminium, it's almost and what we have, do we have timber here? I guess no. No worries. What we understand when we see these numbers, actually E is a material property, a constant material property. That's okay. So if we have higher E value, that means we have really a big resistance to deformation. If we have high E, we have really significant resistance to deformation. So the same section under same loading, aluminum member makes 3 times more deformation than steel. Okay. As you can see, the proportion in between these two numbers is almost 3, let's say 3. The aluminum member makes 3 times larger deformation than steel. So if we have higher E, that means it's a good thing. So steel has really high modulus of elasticity. Yes, you can compare materials with the E values. For example, I don't have an E value for the timber at the moment in my notes, but if I found, I can share with you. Again, steel is greater than aluminum and sorry, timber, basically. Okay, now what we have, allowable stresses, Poisson ratio. Okay. 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 This is another material property. Let's say we have a material like this. If we apply tension to this member, what we are gonna see? Okay, this is the first member, initial shape. Under loading, tension loading, we are gonna see this is P, this is P. As you can see here, this is the initial material. This is the initial material. When we apply tension load, the section area reduced, as you can see. But at the same time, our length of the member increased, as you can see. There is a proportion between this two deformation. In one direction, there is elongation. In one direction, there is a shrinkage, as you can see. The ratio between these two, lateral strain axial strain. Lateral strain is a negative strain. It makes reduction on the section, but axial strain is a positive because it makes elongation in the length direction, longitudinal direction. The result will be negative. That's why in our equations we put here a negative minus here. The result comes out positive. So, but you understand what is the behavior. This ratio is the Poisson's ratio. In structural design, we use this material. This is also a constant material property. We have these values for steel, for concrete, for timber. For each type of material, we have these Poisson ratios. Okay. Okay, we have this one. And here we go. Now, I'm going to talk about the factor of safety. Second, there's something wrong. Share again. Okay. Factor of safety. actually factor of safety, or N, actual strength over required strength. This N should be at least equal 1. Okay, what does this mean? Okay, let's say we have a column here. We have a concrete column. So we are applying on top of this one is EQs 200 kilonewton, and its capacity, load carrying capacity, is let's say is this okay? No. When we look here, the capacity is really low, less than the required one. If we do the calculation, this factor of safety for this one is 0.9, and it's less than 1. That's it doesn't work for us, because our factor of safety should be at least 1, for a design. But what we do, we suggest you 1.3, 1.5, because there will be many different things on construction site. There will be material effect, there will be workmanship effect. We may encounter with different site conditions. That's why we suggest you to use 1.2, 1.3, or 1.5 for the factor of safety in professional life. But theoretically, if we have a factor of safety equal or greater than 1, it works. That's okay. Here you can see we have 0.9. It doesn't work. Let's change the question. If the capacity is here, safety is 1.5. Yes, it works for us. Okay, actual strength over required strength gives us factor of safety. Okay. In design, we will see allowable stresses. It is what you're gonna hear about the allowable stress too many times in this course. Let me show you what it is here. Go. Okay, sigma allowable. The ultimate stress of the material. Take the ultimate stress of material divided to a safety factor or tau allowable. Take the ultimate shear stress and divide it to factor of safety. N is factor of safety, factor of safety. Okay, they don't have to be same, but for example, N1, N2, because this is axial stress, this is shear stress. We learned what they are. What is the difference between the sigma and tau? We know what it is. One is perpendicular to the area, the other one is parallel to the area. Shear stress is parallel to the area. Take out the ultimate stress here and divide it to a factor of safety, get the allowable stress. So in our design, while we are starting our calculation, we consider, we deal with allowable stresses. We deal with allowable stresses. We check our calculated stresses with allowable stresses. That means allowable stress means in this allowable stress calculation, we consider a factor of safety, because this allowable stress comes from an ultimate stress over factor of safety. Okay, keep this in your mind. In next stage, you are going to see many times allowable stresses for sigma and tau. You will see this. Now you know what the allowable stress is, ultimate stress over factor of safety. That gives us allowable stress. For example, if we talk about the allowable force, for example, allowable axial force, what do we do? Oh, no. Allowable load equals load or force. By the way, remember, stress equals P over A, right? This is stress, this is area, this is force or load, whatever. Now, if we are looking for P, we have to multiply these two numbers. So P equals stress times area. If we are dealing with allowable load, area times allowable stress. Allowable stress is, in Turkish, emniyet gerilmesi. Okay. Emniyet gerilmesi. Sigma allowable, eksenel emniyet gerilme. Tau allowable, kayma emniyet gerilmesi. Okay. If you take a look at Turkish books, you're going to see these wordings in the subjects. So allowable load is this, area times allowable stress. In the next stage, we will use these basic steps. Let me take a look what I have more. I guess I complete everything for today. We talk about Poisson ratio, Hooke's law. Yes, all with the. I think we are done today. Okay, ladies and gentlemen, do you have any question at the moment? I think no. Today, what we did, we have just make a soft start to the strength of material. We talk about the concepts, every fundamental step that we are going to use in the next stage in our new subjects. Thank you for joining the class today. I hope to see you next week. Don't forget to study on the moment of inertia calculations. It's really important. In near future, we are gonna use all these calculations. So thank you so much. Take care of yourself. Have a good weekend. Bye bye.
See you hocam.
Bye bye.